Hello, dear students. So, as I have discussed yesterday, we will be starting with reduction reactions. So, reduction reactions, it's a particular type of. There are various type of reactions that happens in chemistry. Out of that, one important type is redox reaction. Redox reaction. So, I request you to go through plus 2 textbook. In plus 1 class, there is a chapter, seventh chapter of the first part of the textbook. Sorry, first chapter of the second part of the textbook. Its name is redox reaction. Please go through that chapter. And we need to recall what is oxidation and what is reduction. So, oxidation could be told as addition of oxygen, or it could be a removal of hydrogen. This is the old concept, and now the concept is loss of electron is what we call oxidation. And here, if you take reduction, it is the removal of oxygen or addition of hydrogen. According to the modern concept, it is the addition of electrons. So, how do you understand whether the electron has lost or electron is added? For that, we look at the oxidation number. So, if there is increase in oxidation number, then it is called oxidation. If there is decrease in oxidation number, we call it as reduction. Decrease in oxidation number or moving towards the negative. Oh, it's decrease in oxidation number only. We call it as reduction. So let's look into the few routine reactions we came across in the previous classes. See here, the alcohol is getting converted to aldehyde. So if you look at the reaction, you could see that two hydrogen atoms are removed. So if you look at the molecular formula, it is CH3O, here it is CHO. So two hydrogen atom or a hydrogen molecule is removed. So what is this type of reaction? It's of course it is oxidation. Alcohol will get converted to aldehyde by oxidation. Then how could it be like when you remove hydrogen? Yes, exactly. It is oxidation, or you can even look at the oxidation number. The oxidation number for this carbon atom it is +1, for this carbon atom it is -1, for this carbon atom it is -3. So you could see a clear sequence of reducing the oxidation number of the carbon atom where the functional group is attached. So this type of reaction is what we call sequence of reaction is oxidation. And here if you take a secondary alcohol, see here you are getting not aldehyde, you are getting ketone. And ketone could be oxidized to ester, or it could be by hydrolysis could be converted to carboxylic acid. So this is again oxidation. Now if you take the reverse reaction, that is what we call reduction, opposite of oxidation. So this part of this type of reaction, this series of reaction must be there in your mind. So alcohol will get converted to aldehyde or ketone as a part of oxidation. The aldehyde and ketone could be converted to ester, carboxylic acid, and even amide, like that. These type of reactions are Oxidation reactions, these are the typical reactions, and the reverse reaction, carboxylic acid to aldehyde or ketone and aldehyde or ketone to alcohol, is what we call reduction reaction. Here you could see a sequence of reaction. This sequence of reaction will lead to the formation of salmefarmol. Actually, this salmefarmol is a anti-asthma drug, and this anti-asthma drug, you could see from where it is prepared and what are the conversions happened during the course of reaction. So you could see that there is a reducing agent used over here, and what change of the reaction happened over here? This keto group converted to OH, and in the next step this part of this pH group has been removed, and there is a addition happened over here. Along with that, reduction also happened here. The reducing agent is hydrogen in presence of palladium, and finally this ester group, this is an ester group, is removed and converted to OH group. It is again reduction. So there are many aspects you have to observe from this sequence of reaction. Here, when sodium borohydride, one of the typical reducing agent, is used, didn't attack any other functional group. It selectively attacked this particular keto group only and converted to OH group. Whereas when you use this hydrogen in presence of palladium catalyst, it didn't attack any this ester group. When you used lithium aluminum hydride, this ester group is attacked and you have got salmefarmol compound. Here, what is the important concept over here you are learning is, there is a term called chemoselectivity. Chemoselectivity. That is the important characteristics of reduction reaction. Means if you wanted to reduce, as you have seen in the previous slide, you can see many type of reduction reaction. In a compound, when you take a bioactive compound, you can't select a particular means functional group like this function, the particular compound. Means bioactive compound will have various type of functional group. It could be aldehyde, it could be ketone, it could be ester, it could be carboxylic acid. But sometime you may require to convert only the ketone to alcohol, not the carboxylic acid, not the amide, not the ester, like that. So chemoselectivity is very important. So if you take an organic reaction, there are three terms that matters. One is chemoselectivity, the other one is regioselectivity, and the other one is stereoselectivity. So chemoselectivity means where the reactant will react. So there are many functional group, on which functional group the reactant is going to react, the reagent is going to react. And the second point is, it could be told like which functional group will be reacted. Okay, which functional group will be attacked? Is it ketone, aldehyde, or ester, like that? Second question is on the functional group where it is going to react. That's what we call regioselectivity. We have seen in elimination reaction, the negative part of the addendum will get added to the carbon atom which has more number of alkyl group. So it's a regioselectivity matter. And the last one is stereoselectivity, how it reacts. Will it be from attacking from upper side or will it be attacking from bottom side? That also we have discussed in some sort of certain type of mechanisms. So here in reduction, chemoselectivity is very important. When you discuss about chemoselectivity, what is that factor that makes the reagent to prefer a particular functional group over another functional group, that matters. You could see another reaction over here. The paracetamol could be prepared. This is paracetamol. Paracetamol could be prepared from this 4-aminophenol, and also it could be from this reactant. And here this amine group is getting acetylated, not the OH group. So if you take this acetic anhydride which is reacting, and it's a nucleophilic addition reaction. So here if you take OH and NH2, the nucleophilicity of NH2 is greater than OH, that's why it is selectively attacking on this position. So the nucleophilicity of this NH and OH determine the chemoselectivity of the reaction. And here if you see, it's a simple hydrolysis. So actually this part could be hydrolyzed and this part could be hydrolyzed. But for the hydrolysis, this will be more preferred. So this is another chemoselectivity. So in reduction reaction, you must be keeping in your mind, chemoselectivity is very important. Now let us look at what factors are driving towards this chemoselectivity. What factors will influence this chemoselectivity? For that, especially we are supposed to learn the reduction of carbonyl compounds. Means reduction of organic compounds containing carbonyl groups. So this carbonyl groups, this is what we call carbonyl group. And depending on the substituents on these two sides, there are various type of carbonyl compounds. It could be aldehyde, it could be ketone, it could be ester, it could be amide, it could be carboxylate. All these compounds are carbonyl compounds. So let's see what factors will determine the chemoselectivity. What is the idea behind, means how the chemoselectivity is controlled. Here I have taken the reduction of aldehyde to alcohol. It's actually ketone. Ketone is reduced to secondary alcohol. The reagent used is sodium borohydride. And in what way the sodium borohydride reacts? Of course, in ethanol, what happens? It will get converted to Na plus and BH4 minus. And this BH4 minus as a whole, it's a species, and it could be represented like this. So it is having a negative charge, and the negative charge is not accumulated on any of the atom. So what happens when a negative charge is accumulated on this species? It is rich in electron density, so it could be called as a nucleophile. And in order to reduce the energy of this reactive species, it will remove a hydrate from this species. So that's what happens over here. This hydrate, electron rich hydrogen atom is available. So please understand there are two terms. One is a proton, which is having a deficiency of electron. Actually, a proton, hydrogen atom, is having one proton and one electron. So once it loses an electron, it is called hydrogen ion, and once it gains one more electron, we call it as hydride ion. So what happens because the species is rich in electron, this hydrate means with an extra electron will transfer to the carbon atom, which is electrophilic. We have discussed previously in many places that the carbonyl carbon atom is electropositive. It is electrophilic. So a nucleophile can attack a carbon atom, and there will be the same time what happens, this oxygen atom will become negative in charge and it will absorb a proton from ethanol, which is the solvent, and now you get a secondary alcohol, and this ethoxide will combine with the, now this is electron deficient, this HBU3, and you get a species like this. And more interestingly, this is again a reducing agent. And we'll come across a point, that is the reduction of the aldehyde or ketone by using sodium borohydrate is operated by nucleophilic addition mechanism. So let me recall few more points. What is, suppose if you take a sodium, let us take the formation of NaCl. So sodium is an atom, chlorine is an atom. What happens? Na will transfer an electron to chlorine, so this will become Na plus, and Cl will become Cl minus. So what has happened to sodium? Sodium has got oxidized. And what happened to chlorine? Chlorine has got reduced. So sodium has got oxidized and chlorine has got reduced. That's how we got NaCl. Now the question is, what made this sodium to get oxidized? It is the chlorine, because if chlorine was not there, if chlorine was not ready to accept the electron, the sodium wouldn't have got oxidized. So the role of chlorine, chlorine is reducing agent. And what made this chlorine to get this chlorine made sodium to get oxidized. So this chlorine is oxidizing agent, and this chlorine has got reduced because sodium has given an electron to chlorine. So sodium is the reducing agent, and sodium is the reducing agent, chlorine is the oxidizing agent. And please understand, the reducing agent will get oxidized and the oxidizing agent will get reduced. This also you must remember. So come back to the point, this is a nucleophilic addition reaction. What is the nucleophile? Actually, this is this hydride is getting added. So what made this carbonyl group to get reduced? That is borohydrate. So borohydrate is a reducing agent. And with this chemoselectivity, what determines the chemoselectivity, if you ask? It is the electrophilicity of this compound, because we are discussing about a series of organic compound which contain carbonyl group. So the electrophilicity matters, and this is a nucleophile. And what makes the chemoselectivity possible, if you ask? It is the electrophilic nature of the carbonyl compound that determines the selection of the reducing agent. So for that, you need to know in what way you can arrange the carbonyl group of various functional group in the increasing order of their electrophilicity. That will make you to determine which reducing agent could be used for which type of carbonyl group. So when you wanted to reduce a carbonyl group which is having least electrophilicity, you may look for a vigorous mechanism. If you wanted to reduce a carbonyl group which has very high electrophilicity, you may have to use a mild reducing agent. That's the point. So here you could see aldehyde. This I have taken from So you could see aldehyde, ketone, ester, amide, carboxylic acid. And here the nucleophilicity is electrophilicity is very high. This carbon is more electropositive because there is nothing to support. Whereas if you take, you need to think about it, why the electrophilicity of ketone is greater than that of ester. The reason is this pair of electron will be in resonance with this carbon. So what happened? The electrophilicity at this point will get reduced. So please remember, this is what the order of electrophilicity of various carbonyl group. And here, just to keep in mind, the sodium borohydride could be used as the reducing agent for aldehydes and ketone, and it's not much preferred for the reduction of ester, amide and carboxylic acid. And sodium borohydride will not work for carboxylic acid. We'll come across that. So hope you understood few basics of the reduction reactions.